Or so I think I can hear myself. Hello, is it a problem from my side? Hello, sir.
Yes, yes, sir.
Sir, I can hear myself.
Why, sir?
I'm hearing myself, sir, while I say something.
No, no, sir. Your audio is fine. Voice is clear.
Uh, but I'm hearing myself. So it's like I speak and it's coming
Sir, you
to
might be
my
using
headphone.
two devices. Sir, you might be using two devices. Please log out from one device and log in using only one device.
Oh, okay. I'll just come back again. Hello? Hello, can you hear
Yes,
me
sir.
now?
Yes, sir. Yes, sir.
Okay, I think, yeah, thanks, sir. That's sorted. Okay, now, so we were discussing about the second layer here. This is the quantum circuit reported in 2017 paper in Nature, and entangling gates plus parameterized single qubit gates. So these are the gates, and it will go. This determines the number of times this is used as kind of depth of the circuit. And this helps us to explore the large part of Hilbert space by changing the parameter here. We'll be able to this kind of a the sequence of gates helps us to scan the large part of Hilbert space. And then the third level of gate is the single qubit gate, which is again X or Y gate. This simply helps to identify if the complement of any state can be a solution or not. So let us say 0 1 0, the complement of it is just flipped 1 1 0 1. Let's say we obtain 0 1 0 here in the second layer, and we want to see if the complement of it can be a solution. We just use the X or Y gate, and then we get the complement state of it, and then we'll see if that's a solution also or not. So all these three levels are repeated as per the requirement, which also determines the depth of the circuit. And basically, we are solving a quantum search problem aided by a classical optimizer. This is the quantum circuit, again guided by the quantum optimizer, sorry, classical optimizer. Okay, now what does it mean? Increasing the second layer n plus x times. So the implications of this kind of scheme setup, uh, what are the things to be noted? Okay, so increasing the second layer to n plus x times introduce the n plus x parameters for the classical optimizer to be solved. So there is a cost associated with it. We cannot just invariably increase the depth of the quantum circuit. So it's like increasing the size of the haystack to find the needle from there. So balance is needed between space, depth, degree of scanning the Hilbert space theta, which determines the degree of scanning, and the coherence time and circuit noise, which is with respect to the quantum computer that we are using. So basically, it's a trial and error approach, basically governed by variational theorem, and increasing the circuit depth may exceed coherence time. So the idea is that we should not have we should have enough number of gates to span the enough search space. But if it gets out of hand, then more gates means more runtime and more noise. Therefore, a balance is needed between the circuit depth, noise tolerance, and number of parameters that we employ. So here usually, okay, now this is where I want to focus on in this lecture, the idea of expectation value. As I said, there are different components in the variational quantum algorithm. Uh, okay, the Hilbert space. So the Hilbert space. Okay, the Hilbert space is a mathematical construct. It's an abstract vector space. Vector space, let us say, we have studied this in our school. Vector space has, some certain axioms. There are rules it has to follow to constitute a vector space, such as, there must be distributivity. The additivity of two vectors should result in a vector that also lies in the vector space, and there are four or five such axioms, right? So this Hilbert space is again a kind of a vector space, where the inner product is also defined. What do I mean by that? Inner product leads to what is called measurement. In fact, we will see that in our in our uh, slide, a later slide. And the Hilbert space is a minimum requirement for such mathematical construct of in a product. Now the point is that the Hilbert space is where the quantum states live in. That's how we can see it. We live in this Euclidean space, and the Hilbert space is a place where quantum states can live in. Right, I hope that answers the question. Okay, now I will go to this expectation value. The components that are involved in the cost function, so the components that are involved in this variational quantum algorithms are cost function, ansatz, and pqc. Ansatz or pqc, and then optimizer. So there is a lot of the cost function, as I said, is a thing that is given to us, so there is nothing to worry about that. It's a domain specific knowledge. And then we have ansatz, which is again can come from what is called hardware efficient ansatz, or problem inspired ansatz. And there's optimizer. All these things are the amount of material available to these kinds of concepts are really high. There are various on the internet. That's what I'm trying to say here. So what is usually not focused is this idea of expectation value, because the expectation value is the metric or the thing that we want to optimize here. So I want to add I have added few slides here that can help us digest the concept of expectation value. Okay, and it is yeah, we've done some mathematical solving here, which I will discuss. Okay, before going to that, I will just paint the significance of expectation value here. So the energy, it's the energy estimation tool. This is the energy estimation engine, and provides an estimate of energy for the system at hand. And in variational methods, the goal is to minimize the expectation value, which is the mathematical optimization problem at hand. And therefore, it is the mathematical optimization also revolves around the expectation value. And the quality of wave function can also be obtained by the idea of expectation value. So that's again metric to understand the wave function at hand. The variational principle ensures that no matter the trial wave function, the computed expectation value will never fall below the ground state energy. Again, this is a mathematical guarantee, so we do not have to worry about the expectation value below the threshold. So this expectation value is applied in many areas of physics, chemistry, etc. So the point is that the expectation value is very important to is an important metric that governs or lies in the uh, quantum algorithms, variational quantum algorithms. Okay, now the mathematics part of it. This is what I want to convey through this lecture. So let us take. I hope the concept of operators and qubit states are already well known to our audience. So now these are the possible operators, two possible operators that can be developed from using two qubit system. So this is one such operator, where there is ket 0 and bra 0, and there are two states that it can act on, which is ket 0 and ket 1. So if we were to, I'm just trying to uh, this is a mathematical result, but we'll paint a physical picture as we go forward. So the idea is, if this operator acts on ket 0, and the inner product of this is 1, therefore we'll end up having 0 here, ket 0. And if this operator acts on the same operator acts on ket 1, this the inner product of this 0 and 1 is 0, therefore this thing vanishes. 0, it's number 0, scalar, no value here. And there's another operator ket 1 bra 0, which acts on ket 0. Again, the inner product is 1, therefore the value is 1. And there's another operator ket 1, the same operator acts on ket 1 state, and it goes to 0 here. So now, what is the physical picture here? So the action of outer products on the qubit states continued. Now, if we were to take 0, 0, acting on x, and if x equal to 0, then we get the ket 0 again back. So which means the state remains unaffected. There is no change. And if x equal to 1, then this is 0. Therefore, the state that we started off with is unhighlighted. So we started off with the state 1, get 1, but it has been destroyed here by act of this thing. So this is called destruction. And then we also have the another operator, get 1 bra 1, which acts on get 0 and leads to annihilation of the state, and the same operator which acts on 1 leads to preservation of the state. I hope you are getting the picture here, the which is annihilation, preservation, and the state remains unaffected, state is destroyed. Okay, now there are two different operators, which is what we saw earlier, which can be called raising and lowering operator. It's usually called together as ladder operators. And when it acts on get 0 state, it will give ket 1 state, which means the energy has raised from ket 0 to ket 1 here, and it is called excitation. And the same operator, when it acts on ket 1, the state to begin with, which is ket 1, is destroyed. There is no state, it's 0 here. Similarly, I remove the lowering operator, which is given by this ket 0 bra 1, acting on ket 0 state, leads to annihilation of the state, and the same operator acting on ket 1 leads to lowering or de-excitation. Because it's called lowering or de-excitation, because we began with ket 1 state and we had to go to ket 0 state, which is lower than the ket 1 state. Sir, in case when we are getting 0, we are saying destroyed, and in case 2, when we are getting 0, we are saying, oh yeah, it's the same thing, sir. I just wanted to say, because these are different ways, just like PQC, variational answers, these are the terms revolving around. I just wanted to say, show that. And destruction or annihilation or creation or things like that. This is also creation. Okay, now a small recap of the gates that we have, so that we go with the flow now. So X is this, which takes care of bit flip, and Y is this, and it does the bit and phase flip operation, and Z is this, which is only phase flip operation. Hadamard gate given by this creates superposition, and phase gates basically phase S is a phase shift of pi by 2. Okay, now why is this important? We'll come to that in a bit. I just want to, before going to that, we also want to construct the outer product notation of these gates or operators. So as you know, this is get 0, get 1, and this is get 1, get 0. This is basically coming out of the outer product notation. And this is the matrix that we have seen here. So now, some circuit identity to equip ourselves for the expectation value calculation. So this is HZH equal to X, and that's what we have proved here. I will not go through the multiplication here because it's straightforward for everybody here. So we'll just skip this. But the point is HZH is equal to X, and then SX S dagger equal to Y, which is again proved shown here. We will not go through the details. Okay, now the Dirac notation, some groundwork before getting into the expectation value again. This is the ket state that we know of, and this is the Hermitian adjoint complex conjugate of the ket state, which is bra. And this is basically the inner product, presents the overlap between the two states. And the inner product conjugate symmetry is this, which is like, we have a bra psi and then ket phi, and the complex conjugate of it is equal to the original one. So the phi, bra phi, and ket size complex conjugate. Is it possible to consider the outer product of any Hamiltonian? Oh, okay, that's an interesting question. Um, Hamiltonian, Hamiltonian. Okay, we'll see. I'll show you how the Hamiltonian comes out to be. The terms come out to be, and we'll see whether there is outer product there or not. Okay, we are looking at the outer product. In fact, we use these kinds of operators to describe, okay, these kinds of operators like raising operator and lowering operator, which is called creation and annihilation operators within quantum mechanics, quantum chemistry. So therefore we can call that as operator being used, but not necessarily outer product. But for our case, we can see whether we'll see whether the outer product shows up there or not. Okay, that hasn't directly answered your question, but one thing is I want to tell you that creation and annihilation operator, which we saw, these are the outer product, building it using outer product. Therefore, they are definitely used within quantum mechanics. In our context, we'll just see whether we are using it or not. Okay, now this is the inner product conjugate symmetry, and this is called conjugate symmetry of the inner product. It means the inner product of psi with phi, right, and in the ket state is the complex conjugate of the inner product of phi and psi. So we have to do the inner product and take the complex conjugate of it, which will be equal to this. So this is the inner product conjugate symmetry that is shown here. So now let's take an example. Take theta, ket 0, and the inner product conjugate symmetry to it is in this fashion. Okay, now this property states that if you swap the order of the inner product, you must take the complex conjugate. Just swap the order, then take the complex conjugate. Otherwise, leave it as such. Okay, that's the go here. And some example here to help us digest. And this is 1i, 2i1, as you can see. And I want to calculate phi psi, and this is the bra phi. So we are going to take the complex conjugate of it, which is this, and then calculate the inner product, which gives minus I, and take psi phi. So we are taking psi phi, the reverse of it. We are not taken the complex conjugate. We are just reversing the states, and now it's ket psi, bra psi and ket phi. So take the complex conjugate of ket psi to obtain the bra phi, which is what we have obtained here, and then the inner product of phi with psi is this I. So once we have the value, and as I mentioned earlier, the conjugate symmetry requires you to take the conjugate transpose after having obtained this calculation, the result of this calculation, which is I. So we take the complex conjugate of it, we end up getting minus I, which is equal to the first inner product of psi with phi. So hence proved with some example. Okay, now the the essential concept here is we have discussed the operator, we have discussed the inner product, we have in the Dirac notation. The most important point here is to see the projection interpretation of this inner product. The inner product of psi with ket 0, the bra 0, is a projection of state psi onto the basis state ket 0. So the idea here is, uh, what does it mean? So we have two channels of photons coming in. I'm trying to paint a physical picture here again. Uh, Psi is the input. Psi is the state that we are given with, or we have developed. It's a wave function, right? So we have parameterized it, not parameterized it, whatever it is. We have a psi, state psi, and there are two channels which are like computational basis. Uh, 0 and 1, and we want to project it onto one of these channels. That's exactly what this inner product helps us to do. So therefore the idea is to see it as the projection of psi, which is our input state, onto the basis state ket 0, and its magnitude is given by this formula. As you know, it's the complex magnitude of any complex number can be given by this formula. And so this leads to what is called measurement in quantum mechanics. Gives the probability that a measurement of psi. Now what is the probability that psi in the standard basis gives the outcome 0, and it is seen in the channel ket 0? So what is the probability that psi is going to collapse to the collapse in the channel, or going to be seen in the computational basis 0? That is what this probability is conveying to us. I'm trying to give the physical picture here. Okay, again, is the same thing. This works because, and now similarly, we want to just an extension, extension here. We have psi projected onto ket 0, and we have a same thing here, but in the reversed order. And this can be seen as a this is, if you were to unzip it or extract it, this is how it will be. And why is this true? That's because of the inner product conjugate symmetry that we already saw. So this is the state that we already have. Assume that it's the ket psi being projected onto the onto the state 0. So we have that here, and we would like to have the same thing here so that we can square it up. And how do we do that? Just by taking the complex conjugate of the swapped order. And the swapped order is this. So we end up getting the square of the this inner product. So again, it shows that it's a projection squared. Okay, now this can be generalized, which I will not discuss now, and just generalized to get one. It's the same result. Okay, now the measurement of a qubit, as I said, this is the how we measure the qubit, and this is the input state that we are given with q, which is where a and b are the complex amplitude belonging to two-dimensional space, and that's the input state we have, and we would like to project it onto the get 0 and 1 basis. And this is how it is done. As you can see, the modulus squared. One important thing to note is here it's the modulus squared, not just a squared. It's a modulus squared, and here also it's a modulus squared. So it's a and b. Okay, and this determines the probability that it will a determines the probability that it will collapse into state get 0, and b determines the probability that the the qubit q will relax into the state 1. Okay, now expectation in value in quantum mechanics, coming to the expectation value now, which is what we wanted to cover here. And if a quantum system is in state psi or q, we want to calculate the expectation value or the average outcome. Basically the average outcome of some observable, any observable. It can be a dipole moment operator, it can be a Hamiltonian operator, it can be a position operator, it can be any other operator, and we associate it with a Hermitian operator. It has to be, one important criteria is that it has to be Hermitian in nature. Hermitian, as you know, is its own self-adjoint. Okay, so this expectation value of this operator is sandwiched between this inner product. That's what I would like to emphasize here. The inner product was there already, and you uh, put a operator in between, then that yields what is called the expectation value. Yeah. Yes, please, sir. Dr. S.G. Dahotri. Okay, if there is no question, I'll move on. Basically, it tells us the average value obtained. No, this has to be repeated several times. This is where the idea of shorts comes into the picture. In when we do the quantum program, we'll assign value to shorts. But the point is that this has to be done several times to get the original right value. And so this is the case where uh, lambda, this is the eigenvalue that we end up with. Okay. Now suppose we'll calculate the expectation. Sir, can you repeat the projection? Okay. The projection, we have all done this in our school. We know that it's we have a vector. We have a vector. Let us say we have a vector, and we would like to cast it onto the x-axis or y-axis. Which means you want to project it on the x or y-axis. It's basically that. And okay, imagine x as ket 0 and y as ket 1. Okay, these are the two axes and also the two states. They are orthogonal to each other, and they, considering they are normalized, they form a valid basis now. Oh, sorry, they are already valid basis. They are orthonormal. Okay, so now the point is, if I have a vector, let us say, which is 45 degree between 45 degree away from x and y, which is respectively 0 and ket 0 and ket 1 respectively, then the coefficient you can write for the vector is half times the x axis and half times the y axis, right? So if you project it, it will be 50 percentage on the x axis and 50 percentage on the y axis. It's basically that kind of a projection that we are talking about here. However, this is just a two-dimensional system, so this analogy works for here now. So basically it's a projection from mathematical point of view. Expectation value of z. Okay, now we are at this juncture where we would like to calculate the expectation value of the operator. So you saw, right, this one z. Z what we z is a Hamiltonian that we would like to sandwich in between the quantum state. The quantum state in our case is kid 0. So we have this, and we do the multiplication, which I will not go through here, and we end up getting 1. So the expectation value of z in the state kid 0 is 100%, right? Because it's the eigenvalue. Therefore, it's we are sandwiching it between these two states in the complex conjugate and kit way, and we're getting it. So the point is that okay, now we'll come to try to answer the question. The point is that since this is Hermitian operator, the observable has to be real number. It will be a real number, and that's what we've got here. Okay, whiteboard. What do you want me to write? I'll try to write that. How do I can okay, I will write. Just give me a second. I'll connect the. Where can I see the pen? I'm unable to spot it. Oh, must be available, right? I think I've done this before. Okay, how else can I, in that case, what open the PDF with other softwares? Okay, okay, maybe what I will do is, let me just try to open. Just a moment, I'll stop sharing. Okay, let me share back. Okay, uh, are you able to see my screen? I hope you are able to see my screen now. Yeah, tell me what. Okay, now. So yeah, okay, now here I'm trying to find orientation of my tab. Yeah, here it is. Okay, where should I look for pin here? Design. Okay, I think this is it. Okay, yeah. Mm. Okay, this is what I'm talking about. So when I say projection, let us say we have two axes, X and Y, and we have a vector which is 45-degree away from here and 45-degree away from here. And I want to, and it's basically, and we are interpreting this as ket 0 and ket 1. So they are orthogonal to each other, which means 90-degree here. Because if we take the inner product, cos theta, cos 90 will be 0. The point I'm trying to make here is, if we want to calculate this projection of this vector psi, that is our input vector psi, onto, we can calculate the projection of this input vector psi onto two states, two bases basically, which is this is our input vector and this is the basis that we are working with, our computational basis. So what I'm trying to say here is, if you would like to mathematically calculate the projection, think something wrong with my setting, I'm unable to scale up. So I'll just write it here. I can project it onto kids 0 state. I have to, because my computational basis is such that it's 0 and 1. Then I have to, then I'm supposed to project it onto the state ket 0 and ket 1, just ket 0 and ket 1. So I am projecting it onto ket 0 and ket 1. Okay. So what I said in terms of photon was, so there is a light coming in and we have what is called beam splitter. Imagine setup, it splits the intensity of the incoming beam into 50 percentage, and it comes like this. There is a mirror here, there is a mirror here, and then it comes back to this position here. This is a mirror, fully reflecting mirror, and we have a detector here in these two directions. Okay, imagine that way. So the point I'm trying to make here is, this can also be considered, this can also be considered as a uh, channel. This is zero channel, this is one channel, the direction of propagation of light. That's a physical picture. In fact, this is called path degree of freedom in quantum mechanics or computing. Path degree of freedom, because we are using path, direction of the path, to encode the information. Okay, this is the projection I'm talking about. I hope you understand that now. And why is it important? Because once you have this and you square it, that's called measurement in quantum mechanics. It's called projective measurement. Mm, and that's what we have here. Okay, and I'm calculating the expectation value here. Okay, that's what we've done. Okay, now now the time is coming to address the question where we'll be using the operator for the Hamiltonian. Okay, so now we know that Z can be written as this in the outer product form. I hope this projection is clear now, and I'm moving on to the next part, which is understanding the operator expectation value. So this is the outer product for as we've already seen, this is the outer product for the operator. So once we have now we have expanded it, which means we are going to use it. So to answer your question, yes, we are going to use it here. I just wanted to come out as a concept rather than just giving an answer, so I thought we'll wait. So again, it's the same thing we are doing. This is the psi input ket vector, which is alpha ket 0 plus beta ket 1, where alpha and beta again belong to complex vector space, such that alpha square plus beta square equal to 1. And the energy associated with it is energy for the expectation value for the z operator can be given by this kind of sandwiching, right? We know that that's what we've been seeing so far. So this sandwiching, and substitute z in the outer product form. Now we have done that here, which means now we have this z, this outer product form acting as the given in the outer product form is the Hamiltonian here, and it is in the Dirac notation. So this is the convenience of the Dirac algebra. And no, so now using linearity, you bring in the psi inside, so that we'll get psi 0 and then psi 0 and then one psi 1 and one psi. Once we have the we know that the complex conjugate of this will we can write the complex conjugate of this. What do I mean by that? So we have, so I wrote as, so I'm writing psi 0 0 psi, right? And rewrite it here. Okay, now we know that we if we want to swap the thing, we'll have to obtain the complex conjugate of it. So we would like to swap this as this and keep this the same as the complex conjugate, or you can write it as 0 psi star here. This is the inner product projection symmetry we were talking about, conjugate symmetry, sorry. And then we have one psi as the complex conjugate. They are same. They are same. This and this are same. And then we have one psi. So basically what we have obtained here is z star z, z star z. So if you remember, z square magnitude for any complex number, say complex number is a plus ib, we have to do z square modulus square, which is this. So we have obtained this part here. So we can now might as well square it. So basically the inner product, which is the projection here, we are squaring it and we are calling it the measurement. And this is called measurement in quantum mechanics. And this is the probability of seeing ket psi in the state ket 0 or collapsing it to the state ket 0. This is the probability of ket psi being collapsed to ket 1. It's the square, it's the Born interpretation. So that's what we end up obtaining here. So that's what have shown here. And why is it important? Because this is exactly where the idea of expectation value comes into the picture. Computability, the way we are going to compute it. So far, we have seen expectation value as an abstract concept, but how do we exactly compute it for our purposes? This is where it comes out in the form of the probability. So we have obtained the probability of p0 minus p1. I hope that is clear. Probability of measuring the state input state in ket 0 and probability of input state measuring the ket state in ket 1. Sorry. So now let C not be. Now in practice, you prepare many copies of psi. As I said earlier, we'll be preparing many copies of psi. And of course, this is not against the no cloning theorem, which you might have heard before, because the no cloning theorem involves, dictates that we cannot clone unknown quantum state. Here the quantum states are known. We know the specific coefficients here, so it can be prepared as many times as possible. There's no harm in that. There's no problem there. The So let C be the C naught be the number of times outcome 0 is observed, and C1 be the number of times 1 is observed. So the probability of obtaining P naught is given by this formula, and there is C naught, which takes care of probability of ket 0, divided by, of course, total outcomes, right? The individual outcome by the sum of all the outcomes here. Therefore, here is where the statistical picture comes into the statistics comes into the picture. So far, we have seen one expectation value as one abstract concept here, but the point is that it will be repeated many times, several times. We might, there is 10,000 or 8,000 shots that are available, and more, of course. And we end up getting a distribution. And that's what this gives. So finally, the expectation value is calculated using this formula. So this is exactly how the energy is calculated for molecules, or while doing portfolio optimization within quantum algorithm. This is exactly what I wanted to convey here today. But yeah, I hope this is clear now, because we'll go to a little more, a couple of more Hamiltonians, and then we'll wind up. Any questions, please feel free to ask now, because the next two Hamiltonians will have a couple of more steps, in order to get here. Okay, I hope this is clear now, and we'll move on. So what is the point? One creates a quantum circuit, that prepares a desired state psi, which is what we want to calculate, and measures the computational basis. In the computational basis, the process is repeated as many times as wanted, and we end up getting C naught and C1, which are basically the distribution, or the y-axis of ket 0 and ket 1, the number of times they have shown up, and therefore from there we calculate the expectation value. This is quantum circuit for that. That is psi, and just measure in computational, because it's the Hamiltonian is Z. Now what about X? That is where the circuit identity comes into the picture, which we have seen earlier. And the idea is that substitute in place of X, HZ H. And now there is a trick here. See, we have obtained this, and we know that H dagger equal to H, because it's Hermitian. It's also the unitary matrix, which means it's self-adjoint. Is its own inverse as well. So we rewrite that in such a way to obtain this kind of a form, just like last time. It's the same inner product conjugate symmetry. Uh, and then it simplifies to obtaining H psi and phi H psi in this fashion. So let us say H psi gives mm, H psi gives what we have obtained here is H psi Z H psi, right? And this is this is this is basically the operator acting on a state, and it will give another state, and the conjugate of it is what we have here. So which means H psi will give psi. Sorry. So we end up having psi z psi. A Hermitian is the nature of the matrix. Hadamard is an operator gate. Hermitian is this, and unitary requires the definition of this. This is dagger. I hope you understand that. So any quantum operator has to be quantum gate has to be unitary in nature. So that is where these things come into the play. So now once we have this, which means like last time we can calculate this, right? So we end up having this, for which we'll again have C0 and C1 coming into the play. And this will be transformed from psi, we have gone to psi dash. And therefore, which means we have calculated using the Hadamard gate here. Okay, so this is how we have to calculate the expectation value, and this is how the expectation value is calculated. Again, another circuit identity which we will not discuss here, we will not go through the proof of, because for the lack of time. But the point is that this is a circuit identity which we will use to calculate the expectation value of y. In fact, you can probably try this at your home. To calculate the expectation value of operator y, we put like this. We arrange h and s dagger within the complex conjugate, and then there is z operator, which because we always want to measure in the computational basis, so we are always converting any operator into the z basis. And on the right hand side we also have h and followed by s dagger. So up through multiple manipulations like last time, that we did with z and x, and we'll obtain this state where z, we end up getting z here. We can manipulate it in such a way. The point is that again we have obtained the distribution in the form of C0 and C1. Therefore, we can calculate the expectation value. So this is the circuit to obtain that. Okay, I am just trying to rush here. Uh, yeah, just feel free to discuss later. Okay, now to compute the expectation value of operator, which is XYZ, and this is how it is done. Z, no gate is needed. X, we apply H gate, and Y, if there is Y, then we apply H and S dagger. And so application perspective, it will be like first the S dagger will act on the quantum state, and then followed by we'll have H acting on the transformed state. Okay. So next thing is, okay, this is important thing I just wanted to convey. This is the 2-qubit Hamiltonian. So let us say we have a Hamiltonian which is X tensor Z. So let's see how it works. So X, in place of X, we substitute the HZH, which we've already done earlier, and Z we are calculating what is the U in the last slide for poly Y. Okay, I'm just calling it U. I'm just, just for the sake of convenience, just algebraic manipulation. I've bundled H S dagger into U. That's all, and therefore U dagger is there. That's all. You can work this math out by yourself. Shouldn't be a problem. It's just I've bundled the thing. So now we have this kind of expansion, and by linearity of the tensor product, we put it like this, we arrange it like this, and apply the conjugation again, H psi dagger z z, which is what we already have, and H tensor I. So this again, identity's dagger is identity, Hadamard's dagger is again Hadamard, is its own conjugate, therefore we end up having this state. So now let us define that psi prime equal to h psi h tensor I psi. See on the right hand side of it, the right hand side part of it, this part, we are calling it psi prime. And so now, which means on the bra, this is the kit. So therefore, we are going to have the psi prime, bra psi prime, right? So this is reasonable to have it psi prime here and psi prime here. And now we expand the operator here in terms of 0 z operator here, which is nothing but 0 0 minus 1 1 tensor 0 0 minus 1 1, which takes care of these two operators, and this is what we have uh, uh, valued as psi prime. So we end up here, and after this is simple manipulation. You can understand it easily. I do the tensor multiplication here, and then we end up getting 0 0 0 0 0 1 0 1 in this fashion, projected onto the states, and then we bring in the psi prime inside, and we end up getting this line. After this, after the manipulation, like last time we did it in x z, we can we can uh, transform this equation into this equation, which means now this is going to act as a probability or the measurement on the z0 channel. This is the measurement on the 0 1 channel. The probability that psi prime collapses to 0 1, the probability that psi prime collapses to 0 0, the probability that psi prime collapses to 0 1, the probability that, okay, I think something wrong here. And while preparing the slide, it's supposed to be 1 1. So finally, we end up getting probability here in this format. Again, the point is that we have obtained, come to this place where we can calculate the histogram or the observation, number of observation. Now, instead of P0, it will be P00, P001, 10, and 11, which means we have obtained the probability distribution, and from there we'll be able to calculate the expectation value. And why is it important? Because all these problems of variational algorithm depends on calculating the expectation value, which is not a matrix diagonalization procedure. We'll end up calculating the exact one, but this is an averaged out one, and therefore needs to understand how it is calculated within any function like Qiskit estimator or sampler that we have. Okay, these are the references. This is one of the first papers of variational quantum eigensolver using photonic processor, and this is the 2017 paper. Uh, I think so, and yeah, and seems to be the paper. Okay, these are other papers from where I got some concepts. Mm, yeah, and then there is a Penny Lane website, and then there is a IBM Qiskit website. Yeah, I think there's a message. Please share it. Yes, yes. This canvas one. It's in. Thank you. It's in the PDF format. I will share it with you. Okay, this is my email ID. Feel free to engage if you have anything. Okay. Thank you. Please ask questions if you have any. I had prepared a couple of Jupyter notebooks, but I think we are over time now. Or if you want, I can show you that as well. Yeah, the point is I wanted to thank you so much. Impress upon the idea of expectation value. Understanding the Hamiltonian or the ansatz is very much available in the internet. But okay, one important thing I forgot to mention. There is uh, okay, yeah, the idea of understanding the expectation value is important to get the averageness. Yeah, the mean picture of the average picture of the quantum mechanics and the quantum computing. Thank you. Okay. Any questions? Please feel free to ask. Thank you, sir. Thank you all.
Thank you so much, sir, for this wonderful session.
Thank you, sir. Okay, thanks everyone for listening. Thanks, Dr. Emmanuel, for arranging this. Thank you, JV. Okay, thank you, uh, everyone. Okay, okay, yeah. Sir, should I stop and log out? Can I? Why is it important for the initial? Okay, okay. Yes, so that's a very good question. The reason is in QP, it's not an iterative process. There is no uh, room for parameterization. We are not parameterizing it, but there is something called iterative quantum phase estimation. We are not talking about that here. So in QPE, given that there is no parameterization, we have to have the quantum state, which is already in uh, high degree of overlap with the state that we want to find. So that's the requirement and the flip side. But otherwise, calculating the expectation value is the beautiful part in the QP. So sometime when the quantum computer is high, really high, I mean really robust and with lots of qubits, QP will take over. If yeah, okay, okay. Thank you then. Thanks everybody. Sir, can I log out then, or what? Should I wait for something?
Yes, sir. Sure.
Okay. Thank you very much. Bye, sir.
Thank you.
Thank you all.